Okay, today's video is on the electronic structure of atoms. So we're dealing with those weird little electrons. So it started off thinking about light, and we really thought that the world was in two realms. We had the realm of mass, and we had the realm of energy or particle and wave. And those two realms did not intersect. So scientists, all of our thought here kind of started with what is light? Is it a particle or is it energy? Does it behave like a piece of mass, or does it behave like a wave? And we ended up designing experiments to test it and coming to the conclusion that yes, it's both a particle and a wave. We had to get Einstein involved in all of this, and he came up with the wave particle duality of light, that it is both energy and matter. And that didn't sit very well with a lot of scientists, but it's something we had to accept because we do like to categorize things. So light is both a wave and a particle. So it behaves as mass and it behaves as energy. And it really depends on how you look at it as to how it actually behaves. And what we learned from light, we could apply to electrons because they are, we tend to think of them as particles. Like we draw our models of the atom and we put a dot there and signify that as a particle. But what we find out is that electrons also behave as waves, and often more behave as waves than they do particles. And so coming to this conclusion really helped us to formulate that quantum world or quantum mechanics of the atom and how we think about those subatomic particles. Now, since light does behave as a wave, you need to know a little bit about a wave. So you've got crests, which are the top of the waves, and troughs, which are the bottom. So crests and troughs. And we have our wavelength, which is measured from crest to crest or trough to trough. And it is represented by the Greek letter lambda. Lambda is wavelength, and you need to get that associated in your brain. And it is, again, measured from crest to crest or trough to trough, and is measured in meters or nanometers. A lot of times we use nanometers in chemistry because we're talking about wavelengths of like visible light. Now, another concept about waves is frequency. Frequency is the number of cycles or waves in a second. And so it's going to be measured in hertz. So that's Hz is what its abbreviation is. We will represent it by the letter V here. And so here I have, let's say the screen, I have 1 second of time. So this particular wave has three waves happen in a second. Well, if I increase that frequency and have more waves per second, you will notice that my wavelength decreases as frequency increases. So they do have that opposite or inverse relationship to one another. Frequency goes up, wavelength goes down. Now, the other thing you need to know about frequency has to deal with energy. Energy and frequency have a direct relationship. So the higher the frequency, so these bottom waves right here at the bottom, these have high energy, high frequency waves. These very low frequency, low energy waves. Now, electromagnetic radiation is energy with wave-like behavior. It sounded way more serious than that when we call it electromagnetic radiation, but it's energy that travels through space as a wave, and it will have electric waves at 90-degree angles to magnetic waves. There are lots of different types of electromagnetic radiation, and we can see that we have radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. I really like this particular graphic because it does have that wavelength in here. So you get a nice visual on your wavelength dealing with these different types of waves. So we can see gamma rays, high frequency, high energy, very short wavelength, as opposed to radio waves. Radio waves have this long wavelength, low energy, low frequency. Now, you will need to remember the relationship between wavelength, frequency, and energy. On your chemistry reference tables, on the very, very last page, you have a copy of this electromagnetic spectrum. It has the same things: radio waves, microwaves, infrared, which has to do with heat, and that tiny little piece that we can actually see, ultraviolet, X-rays, and gamma rays. It doesn't have a picture of the wavelengths, but it does tell you that on this side you have shorter wavelengths, and on this side you have longer wavelengths. And this is why you have to remember the relationship. So gamma rays, if they have a short wavelength, they have a really high frequency. High frequency, high energy. So both energy and frequency are inversely related to wavelength. Again, radio waves, long wavelength, small frequency, small energy. And it can be applied to the colors of the rainbow down here. All right, so like I said, we had different experiments to prove things about light. We had an experiment to prove it was a particle, and that's the photoelectric effect, where they were shining different colored lights on metals to see if they could get them to eject any electrons. Once we got to like purple colored light, yes, it did. Any other color, no. So that proved that light was a particle. Light as a wave, we used the double slit experiment. And this is where we put a wave and made it go through two slits in a wall. This video is a piece of a larger one, but it does a really, really nice job of explaining the double slit experiment and what you can actually see. So we'll watch this for just a second.
Here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples in the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks and peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
It's basically the same as like having two drops.
Okay, so really this is the experiment that proved that light behaved as a wave. If you take light and shine it through two slits in a wall, you don't get two beams of light hitting the back wall. You end up with that interference pattern, and that can only be explained by light behaving as a wave. Electrons do the same thing. They create that interference pattern, and so they behave as a wave. Unless we're looking at them to behave as a particle, then they behave as a particle. So really weird. All right, so let's talk about the energy associated with electron transitions. All right, so two terms you're really going to need to know. You're going to need to know ground state and excited state. Ground state is the lowest electronic energy state. So this ground state follows the atom is following the Aufbau principle. All the electrons are in the lowest energy orbital that can receive it. All of the electron configurations that we have done so far have been for ground state atoms. All of those electrons are in the lowest energy orbital that can receive it. Now, an excited state would be a state with energy greater than the ground state. Electrons are going to, or atoms can absorb some energy, and the electrons will move to a higher energy state, either energy level, energy sublevel. And that's called the excited state. Now, An atom can move from one energy state to another by absorbing or emitting a photon. So they can absorb energy and move to a higher electronic state, or they can release energy and move to a lower one. So when a photon of energy is absorbed by the atom, it moves from a lower to a higher energy state. So I found this little video clip here, and it's a little girl eating cotton candy. And just to show you what that amount of sugar is going to do to a little kid. Look at the wide eyes. You can already see it from here, but let's show you this. Okay, so she has moved from the ground state to the excited state by absorbing some of that cotton candy. And I'm going to keep going with this analogy because we all know that this little kid is going to crash later on in the evening because she's on a sugar high right now. She's at that excited state and she can't stay there very long. She's going to give off a whole lot of energy and then she is going to crash out and sleep the whole way home. So the same thing kind of happens with electrons. For an atom absorbs energy, moves to an excited state, but it can't stay there very long. And so for it to return to a lower energy state, it has to release some energy. And that energy is in the form of photons, so wave-like behavior. Since it is waves, it has a wavelength, and sometimes that wavelength is within our visible spectrum, and we can see that energy that's being released. Okay, so what I was just talking about was in words, and now I'm going to show you in pictures. So here I have an atom with the electrons in the ground state. So all the electrons are in the lowest energy orbital available to receive it. Now I'm going to give it some energy, and I'm going to give it energy with fire. I could also use electricity, but I like this cool fire graphic better. So I add some energy. The electrons are going to absorb that energy and they're going to move to a higher energy state. So now I colored them purple. So they've moved to a higher energy state. And so they've gone up energy levels or energy sublevels. They can't stay there very long. So what's going to happen is they're going to return to a lower energy state by releasing some of that energy. And now you see the electrons have moved back down, but they have to give off energy. So it's really important to know which way the electrons are moving when light is given off. If light is given off by an atom, that means the electrons are moving down energy levels or sublevels. If you give an atom energy, the electrons move from that ground state to an excited state. So they move up energy levels. All right. Now, we're going to talk about specifically a hydrogen atom and that Bohr model. Now, we follow the quantum model and we've learned about the quantum numbers and that sort of thing. And it all started, though, from that Bohr model. We don't use Bohr's model anymore because we found that it didn't really work for larger atoms. But it works for hydrogen still to this day. Now, Bohr decided to use hydrogen because it was a very simple atom. It has one proton and one electron, so we don't have to worry about the other ones involved there. And he made some very interesting discoveries in looking at hydrogen through a spectroscope. All right, so 1913, Niels Bohr developed a mathematical model for the behavior of electron in the hydrogen atom. And he used a spectroscope. This is a picture of his spectroscope that he used. Now, a spectroscope is something that will break light up into its component colors, so kind of like a prism. And he used a spectroscope to look at different atoms as they were being excited. Now, it's hard to isolate one atom, but we got really good at creating glassware so that we could have sealed tubes filled only with one type of gas. So he had a tube of hydrogen gas and he hooked some electricity up to it and it started to glow. And if you remember, that's how we ended up discovering the electron. Is with that glowing particle that happens when you hook a tube filled with a gas up to electricity. Well, he looked at this glowing tube through his spectroscope. And he found that the spectrum was not continuous. He thought he'd see a rainbow, a continuous spectrum, but that's not what he saw at all. What he ended up seeing was more like this. Now, this isn't hydrogen. This is another element. I'll show you hydrogen in here in just a minute. But it's going to be pretty much black, and all you see are discrete lines of definite wavelength. So that means you've got lines of different colors there, and different colors have different wavelengths. And when he looked at hydrogen versus helium versus lithium versus boron, he found that they were all different. And so each element has its own characteristic spectrum. This is like a fingerprint for atoms, and we can figure out what things are based on their line emission spectrum. This is how we know pretty much everything we know about stuff in space. We know that the sun is made of hydrogen and helium, and we know that by looking at the spectral lines. And we can see the fingerprint for hydrogen and the fingerprint for helium. Now, this is what hydrogen's spectrum actually looked like. So when Niels Bohr excited hydrogen atoms, this is the spectrum he saw through his spectroscope. So really just 4 lines. And these lines result from when an excited electron gives off energy in the form of light, it goes to a lower energy state. And we can see that energy of light that's being given off. So this is called an emission spectrum because these are the wavelengths of the photons that are given off by an atom as the electrons move to a lower energy state. So that part right there is pretty important for you to know. So emission spectrum, it's the wavelength of the photons given off as the atoms move to a lower energy state. And we call it a line emission spectrum because they are lines. And they're different for every single element. So here I'm going to show you a Bohr model. And when we're going to look at one that's on your reference tables as well. We've got to be able to interpret it. So when I have a sealed tube of hydrogen, I don't just have one hydrogen atom. I have multiple atoms, and some are their electrons are going to get more excited than others, and they might transition. Some might give off a lot more energy than others. So I'm just going to talk about what we could actually see in the visible region, and I'll show you what happens outside of the visible region. So hydrogen only has 1 electron. So 1 atom, and in the ground state, that electron would be here at n equals 1. And we do use n to represent our energy levels. So in the ground state, that 1 electron for hydrogen would be here. Well, let's say one of my hydrogen atoms takes its 1 electron and it absorbs quite a bit of energy. Let's say it absorbs 2 photons of energy. Then when that excited electron drops down, it only gives off 1 photon of energy. That corresponds, its wavelength is in that red region, so around 700 nanometers in length for that wave. Now, if say another atom, we have an electron that absorbs 1, 2, 3 photons of energy, and when that excited electron drops back down, it gives off 1, 2 photons. They're going to give off a energy with a wavelength that corresponds to this teal color. So 550, somewhere around in there. In another atom, let's say this electron gets really excited. So it goes up 1, 2, 3, 4, absorbs 4 photons of energy, and then that excited electron gives off 3 photons of energy. That's going to correspond to that blue color that you would see in the spectrum, the line emission spectrum for hydrogen. So around 500 or so. And then I didn't draw this one on here, but if an electron gets excited to the 6th energy level and then drops back to the 2nd, that's going to give off that purple color that we would see in the line emission spectrum. All right, so let's look at what you would see in your reference tables. So this is the Bohr model for hydrogen. Looks very similar to what I just drew. It does include other things. So it includes that visible spectrum, which we were talking about here. There's those 4 lines there. But it'll also talk about the UV spectrum and the infrared. These transitions we would not be able to see with the naked eye, these electronic transitions or the energy given off from those, but we could measure it with an instrument. All right, so what we've got here are lots of different atoms kind of laid on top of one another, and you're seeing all the possible electronic transitions for the 1 electron of hydrogen. So if an electron, again, would in the ground state would be at n equals 1, absorbs 1, 2, 3 photons of energy and gets excited up to n equals 4. So where the dot is where the electron's excited to, and then the arrow points to where it drops back down. That would give off a wavelength of light that we really wouldn't be able to see because it's outside of our visible spectrum, but it's got 97 nanometers in length. Here in the visible spectrum, here we have an electron that's been excited all the way up to n equals 6, so that's 6th energy level. And when it drops back, it doesn't drop back to n equals 1, it drops back to n equals 2. That's going to give off a wavelength of light that corresponds to 410. So that's that purple color that we were looking at just a few minutes ago. Now, if we didn't already know that it was purple, we could use the bottom of this same page on our reference tables and figure out what color it is. Now, there is a difference in units. So this is measured in nanometers. This next one is measured in meters. So the transition we saw was 410 nanometers. So down here, we're going to look for 4.1 times 10 to the negative 7. So that's going to put it here in that violet region. So that would be purple in color. This electronic transition that gave off a wavelength of light of 656, we look for 6.56 down here at the bottom, and that puts us right here at this red-orange or orangey red. All right. And that's how to use the back of your reference table. We'll have some practice with that. Okay, this is going to be the end of this particular video, and we'll pick up with the quantum mechanical atom tomorrow.